Kemudian untuk peserta itu video ditampilkan oleh panitia atau peserta presentasi pakai slide. Cek. Masih.
Screen.
Okay, we wait for the committee. Cek panitia.
Pakai ini Pak, pakai slide peserta.
Oh, pakai slide peserta. Oke, baik. Okay, let's start the session. First of all, welcome to International Conference on Industrial, Electronic, Robotic, and Informatics, ICIERI 2024. I would like to thank you all participants for joining this parallel session. Let me introduce myself. My name is Hari Makfiro. You can call me Mr. Hari, and I will be your session chair. Before presentation, I will be read the rules. Here we will have 6 presenter that will present their results. Before beginning the session, the rules are: 1, each presenter is given a maximum 10 minutes to present and 5 minutes for a Q&R. And okay, this you can see the order of the presenter. We follow this order. If the presenter is not come yet, we go to next presenter. Then okay, let's begin the presentation. I would like to invite the first presenter with the title Automation and Improvement of the Artisan Yogurt Packaging Process, a simulation-based approach. For the presenter, for the first paper, times is yours. You can start your presentation.
Yes. Can I share my screen
Yes.
to show my PPTs?
Not yet, not yet.
Okay.
Please try to share your screen again.
Okay. Yeah, I can share. Yeah.
Okay.
Can you my screen?
Okay, we can see clear, and you can start your presentation.
Okay. Okay. Good afternoon, everyone. I'm pleased to present my work. The first author is my person, Jose Gregory Juan Calvino. The second author is Shamir Efraín Salomón Pase. The third author is Max Anderson Inga Gomez, and the last author is Manuel Michael Verón Espíritu. Okay, yeah. The name of our work is automating artisanal artisanal yogurt packaging, a simulation-based approach. This study tackles the challenge faced by small dairy producers in Junín, Peru, of competing in a growing market while preserving artisanal quality. We developed a prototype using SolidWorks for 3D modeling and CARESIMO and PCSIMO for electrical design. Our automated system efficiently handles the filling, taping, and sealing of yogurt containers with precision. This automation enables local producers to enhance productivity, reduce costs, and maintain high product quality, marking a significant step toward modernizing artisanal yogurt production in the region. In the next slide, we can have let's look at the dairy industry landscape in the Junín region of Peru. Many yogurt producers in Junín still rely on artisanal methods, which bring challenge in terms of efficiency and competitiveness. A lack of industrialization knowledge and limited access to electricity in some areas has further restricted the adoption of advanced techniques. The dairy industry is essential to Junin's economy, especially in less economically active areas. In 2014, the region produced around 46,724 tons of milk from 31,721 milking cows. Approximately 80% of this milk was sold fresh, while the remaining 20% was processed into dairy products. Yogurt production in particular has shown steady growth, with an annual increase of 6% since 2015. Natural yogurt has been especially popular, achieving an impressive 11% increase over the previous year. These statistics highlight both the importance of dairy production to Junin's economy and the potential for growth in the yogurt sector. This underscores the need for automation to enhance efficiency and competitiveness for local producers. Okay, in the next slide, in this section, I will discuss the key challenges faced by artisanal yogurt producers in Junín region. The first is time inefficiency, that manual bottling and selling are time consuming, limiting productivity and slowing down the entire process. The second is quality inconsistency, that hand filling leads to variations in product volume and seal integrity, which affects both shelf life and consumer trust in the product. The third is the limit capacity. Without automation, product volume is restricted, making it hard to scale up to meet market demand. And the last one is the research wastage, that inaccurate filling results in product loss and increased packaging costs, adding to overall inefficiency. These issues highlight the need for automation to enhance efficiency, consistency, and scalability in yogurt production. Okay, the automated yogurt packaging system enhances efficiency and precision through key components. A programmable logic controller, that is PLC, manages the process, coordinating sensor inputs and actuators. Solenoid bulbs ensure accurate yogurt flow during filling, while capacitive sensors detect bottles and trigger subsequent actions. A conveyor belt moves bottles through stages, and pneumatic cylinders provide precise caping and sealing. In summary, the system integrates a PLC, capacitive sensors, solenoid bulbs, and a conveyor belt, and also pneumatic cylinders to create an efficient packaging solution. This part is about the simulation and modeling methodology. The development of the automated yogurt packaging system relied on advanced simulation tools to optimize design and functionality. SolidWorks was utilized for detailed 3D modeling, allowing us to visualize the assembly in real time and refine the design before moving to prototyping. For the electrical design, Caresimo was employed to create accurate diagrams that ensure proper system integration. Additionally, PCSimo simulates system behavior under various conditions, enabling us to assess efficiency and functionality prior to implementation. This simulation and modeling approach played a critical role in ensuring that our automated system meets the required standards to performance and reliability. Okay, in the next slide is the automate filling and packaging process. The automate filling and packaging process significantly improves upon manual methods. It starts with bottle detection using capacitive sensors, which trigger the filling sequence. Solenoid bulbs then regulate the yogurt flow, ensuring precise and consistent filling, minimizing waste and maintaining uniformity. After filling, bottles move to the capping station, where a cap dispenser and pneumatic actuators place and secure caps. Throughout the process, the PLC monitors operations, adjusting based on real-time sensor inputs for optimal performance. Some case steps include the bottle detection, that capacitive sensors identify bottle presence, the filling, that solenoid bulbs control yogurt flow for accurate dosing, the caping, that automate cap placement and sealing with pneumatic systems, the quality check, that is the final inspection for filling and sealing accuracy. This system enhances efficiency, accuracy, and product quality in yogurt packaging. About the simulation results and performance analysis. These simulation results of the automated yogurt packaging system revealed significant enhancements in efficiency and consistency compared to manual methods. The key finding includes filling accuracy. The automated process achieved an accuracy of 1%, a remarkable improvement of 80% over the manual process, which had an accuracy of 5%. Packaging speed, that automation increased packaging speed to 60 bottles per minute, a 200% improvement compared to the manual speed of 20 bottles per minute. Error rate, that automated system reduced the error rate to 0.5%, marking a 90% improvement from the manual error rate of 5%. These improvements led to accurate filling and proper packaging for each other bottle, ensuring a continuous production flow. The simulation also highlight areas for further optimization, such as refining filling and packaging times, and implementing additional quality control measures. These enhancements could further increase production capacity and reduce operational costs, underscoring the effectiveness of automation in yogurt packaging. The last part of this presentation is the conclusions and future implications. The simulation-based approach to automating artisanal yogurt packaging in Junín, Peru, has demonstrated significant potential for improving the local dairy industry. Key benefits include the improved efficiency. There is a substantial reduction in production time and labor costs. After this is the enhanced quality, that the system ensures consistent product quality and packaging integrity. Third is the market growth, that increased production capacity positions local producers to meet rising demand. And the last is the industry modernization, that this initiative serves as a model for automating traditional food production methods. Well, looking ahead, this successful implementation of This automated system could inspire similar advancements in other small-scale food production operations in the region. It represents a crucial step toward modernizing traditional food processing, potentially benefiting rural communities economically. Future research should focus on further optimizing the system, exploring eco-friendly packaging solutions, and developing adaptive control systems to accommodate various yogurt types and packaging formats. In conclusion, the automation of yogurt packaging not only enhances efficiency and quality, but also paves the way to sustainable growth in the dairy industry. By embracing these innovations, we can empower local producers, drive economic development, and ensure a competitive edge in a rapidly evolving market. Thank you for your attention.
Okay, thank you very much, Mr. Jus. Uh, is there any question or comment from other participant? Not yet. If not yet, I have one question from me. From me. My question is, what is the most difficult part to do this research? Because you have some step like filling the bottle, put the cap, and other. Based on your experience to do this research, what is the most difficult part? Thank you.
I think that I can find some limitations when I use the simulation tools to develop this solution. Also, simulation is very useful. It doesn't always reflect all real factors, such as potential variations in yogurt temperature or viscosity under different conditions. This requires us to adjust certain parameters during physical implementation to better reflect the production environment.
Okay, thank you very much. That's all from me. Thank you for Mr. Chus for this time, and this enough for you. Okay, thank you very much.
Thank you.
Okay, we will go to next presenter with the paper title Design and Mechanical Simulation of a Solar Photovoltaic Fish Storage Cold Storage Chamber using VDI 2221 methodology. So for the presenter of this paper, please you can share your screen to start the presentation.
Good afternoon.
Good afternoon. Please share your screen. Okay. You can slide show. Please choose the big view. This is like two view. Just tap the share screen. Okay. Okay, you ready?
I can start.
You can start your presentation.
Okay. And good afternoon. And design and mechanical simulation of a solar photovoltaic fish storage cool store chamber using BID 2221 methodology. And the members, the group is my person, Rolling Yazar Quispe Palpa, and José Daniel Cincha Franco, Freddy Miguel Capcha Ospina, and Manuel Michael Bebaun en Espíritu. And the fishes industry face a significant challenge in the preservation and transport of fresh fish due to its highly perishable nature. Maintaining fish in optimal storage conditions is crucial to ensure product quality and prevent economic loss. And conventional cold storage, although effective, often release no renewable energy source, which increases both operational cost and environmental impact. In response of mm, the search for energy efficient and sustainable solutions has gained considerable attention. In this context, in the integration of cooling systems using solar photovoltaic energy offers a promising alternative. These systems not only decrease dependency of fossil fuels, but also reduce greenhouse gas emissions, contribution to climate change mitigation. However, the effective design and implementation of such systems requires a rigorous methodological approach to ensure their efficiency and flexibility operation. And methodology and design process. The design process for the solar photovoltaic a fish storage cold chamber and dress strictly to the BID 2221 methodology, a German start for systematic engineering design. This approach provides a structured framework for problem solving and ensure clear the methodology encompasses several key stages, including problem analysis, conceptual design, and detailed design place. By following this systematic approach to research, then can effectively identify optimal solutions and evaluate them in an structured number. This methodology is particularly crucial when dealing with complex systems that integrate technologies such as solar power and refrigeration. In, in the method, why problem, understanding the application, state of technology, list of requirements, work a plan, and solution concept, function structure, solution concept, project development, uh, preliminary projects, optimal preliminary projects, calculation report, and final design, assembly drawings, and elaboration of details, exploded drawings, manufacturing drawings, assembly instructions, manufacturing instructions, and finally solution. Black box and white box analysis. Black box and white box analysis are essential in designing the solar photovoltaic fish storage cold chamber. The black box approach offers an overview of system inputs and outputs, way to detail internal processes, clarifying system requirements and performance. Conversely, the white box is analysis examined in internal operations, detail component interaction to optimize and elements and ensure seamless subsystem integration. In the black box, white input and thermal energy, mechanical energy, room materials, and photovoltaic energy.
Sorry,
And
sorry to disrupt your presentation, but your slide is just slide one, no changes.
what?
Yes, your presentation slide just show slide number one. Just click slideshow. Like this is better. Okay. Because previously no change. Okay, you can continue.
My presentation not visible?
Now is
Bro,
okay. Now is okay. Before it freeze, but now is okay. Please continue the presentation.
In the white box?
bro, continúa tu exposición porque tus PPTs no se estaban pasando, se estaban quedando en solo la diapositiva de inicio. Ahora sí ya puedes continuar.
Okay. White box approach is fundamental to understand, control, and optimize all internal aspects introducing mechanical simulation of solar photovoltaic refrigeration chamber for fish storage. This method allows for the implement of storage parameters, ensuring the consistency and quality necessary for optimal fish preservation. Uh, uh, Morphological matrix and alternative solution. The morphological matrix is essential for exploring and icing component combinations in dicing. There are alternatives, so three alternative solutions for the cold storage chamber will create wide different combinations of photovoltaic panels, batteries, and refrigeration components. Evaluate based on technical and economical criteria to find the optimal design. No? Solution one. Uh, the fish the fish is fed into the refrigeration chamber manually by means of jigs. The centrifugal evaporator is used in installations where a higher air pressure is required for its conduction. In this case, amplified inside the refrigeration chamber. And solution two, the fish is transported manually in hubs inside the refrigeration chamber. A cubic evaporator in used, designed for storing fresh and perishable products at temperature above 5 uh, grade Celsius, as well as frozen storage, packing workrooms, and freezing tunnels. And why solution three, the fish feed the covering chamber is done manually by means of fish feeders. The roof evaporator is responsible for heat exchange between the refrigerant fluids. The semi-hermetic compressor is designed to offer space. The condenser is intended to dissipate to heat compressor. How these components are implemented in the curved monocrystalline solar is instantly which captures solar energy and generates electricity. A charge controller stabilizes in the electrical produced by the photovoltaic panels. And optimal solution based of technical and economic evaluations. But solution two emerged has the most promising design, balancing performance and cost effectiveness. And simulation setup and initial condition. The simulation of the solar photovoltaic fish storage cool chamber was conducted using advanced computational fluid dynamics CFD software. The initial setup involved defining the chamber's geometry, including the dimensions and layout, the refrigeration components, the simulation into account the effects of gravity and the properties of the refrigerants. Uh, Initial conditions were set to reflect realistic operational parameters, with a working pressure, pan internal temperature target or for degrade 25 grade Celsius, the boundary conditionals, and grade 1 geometry definition. Create detailed 3D model of cold chambers and components. 2 and material properties define properties of chamber materials and area. 3 boundary conditions set inlet outlet conditions for refrigerant flow. 4 mesh generation create heat quality computational mesh for aqua results. 5 solver setup configure CFD solver parameters for optimal conversions. And simulation results are empty chamber. The initial simulation of the empty refrigeration chamber yields significant insights into system performance conducted in over notably the internal temperature of the evaporator was recorded at the grade 14 grade Celsius, indication efficient heat transfer from the chamber to the refrigerant. The simulation also provided value data on the flow patterns refrigerant within the system, allowing for optimization of the refrigerant circuit. Simulation results. Chamber-wide Havas. A second simulation analyzes the refrigeration chamber's performance when load whitefish container. This is complex scenario involved and over 10 hours, 14 1 minutes and 7 seconds, reflecting the increased computational demands. Results show the system ability to maintain optimal storage condition, researching a minimum temperature of degrade 22.81 degrees Celsius, exceeding to initial target and ensure excellent preservation for the fish. The simulation also highlighted airflow patterns within the Leyden chamber, showing how the halves impact temperature distribution and cooling efficiency. And temperature, minimum temperature of degrade 22.1 grade Celsius, archived in Lloyd chamber. Duration 10 hours, 14 minutes, 7 seconds of simulation time. Interactions and airflow. Optimized air circulation patterns around in the containers or hubs. And conclusions and future directions. The design and simulation of the solar photovoltaic fish storage cool chamber have yielded promising results, demonstrating the feasibility and efficiency of integrated renewable energy with advanced refrigeration technology. PIT 2221 methodology provided a robust framework for systematic design and optimization, resulting in a system capable of maintaining optimal storage conditional for fish preservation. Um, One, efficiency design process, and BIT 2221 methodology facilitates systematic development and optimization. Two, performance validation. Simulations confirm ability to maintain optimal storage temperatures. Three, sustainable impact. Integration of solar PV technology reduces carbon from paint or fish storage. And four, future enhancements, potentials for future efficiency improvements, and smart technology integration. That's all. And thank you.
Okay, thank you for the interesting presentation. You have interesting research. And now for the question, is there any question from participant? Because we have limited time, just one question. Not yet. If no, I want to ask about the black box and white box. You choose a black box or white box, and why? Hello?
Repeat the question, please.
You choose white box or black box, and why?
Uh, I am use uh, I am use the level his method more efficiency.
Uh, okay, that's nice. Thank you very much.
Yeah, thank you.
Okay, you can see your screen share. And thank you for Mr. Brolin. We will go to the next presenter. The third presenter will deliver a paper with the title Impact Electromagnetic Stimulation on the Sustainable Germination of Rabanus sativus seed, a multidisciplinary approach. Therefore, for the presenter of this paper, please share your screen. Okay, for third presenter, Mr. Manuel, please share
Yes.
your presentation screen.
Excuse me. Wait a minute, please.
Okay. Uh, if you okay.
Yes.
Okay. Please tap the slideshow for bigger view. Slideshow.
Okay.
Okay.
Good
You can
afternoon.
start your presentation. Okay.
Good afternoon to all present. First of all, I would like to thank the first International Conference on Industrial Electronics, Robotics and Informatics for the kind invitation. Well, my name is Manuel Verón Espiritu. I'm in charge of the presentation of research entitled impact of electromagnetic stimulation on the sustainable germination of Raphanus sabatus seeds, a multidisciplinary project. The research, this group is Katie Moscoso Bocarchuco, Luis Visurraga, Wilfredo Paco Omaní, Shalin Caraboyanqui Ávila, and Joaquín Machaca Rejas. First, the project focuses on addressing the challenges in the seed germination process, exploring environmentally friendly solutions based on physical and biological treatments. It focuses specifically on the germination of seeds of Raphanus sativus, common called rabbit, and analyzes the impact of electromagnetic stimulation on this process, considering the use of technologies based on magnetic fields and ultraviolet light spectra. First, in the seed germination process, the interaction on various factors, both internal and external, plays a crucial role in determining the success of germinating and the subsequent growth of plants. The quality of seeds, soil preparation, and environmental conditions are key aspects to be considered. However, over time, the use of chemical compounds in agriculture has posed challenges running from nutritional imbalances to the inhibition of the growth of beneficial microorganisms and alteration in the taste of crops. In this context, there is a need to explore environmentally friendly solutions based on physical and biological treatments to improve the germination process. This project focuses on addressing this challenge, focusing on the germination of the seeds of Raphanitus sativus, commonly known as raven. The impact of electromagnetic stimulation on the seeds, their effects on the germination process is sought to be analyzed. Furthermore, the use of technologies based on magnetic fields and spectral visible ultraviolet lights is considered as environmental friendly and economical alternatives. This article not only addresses an issue of agricultural and food relevance, but also focuses on commitment to sustainability and environmental protections. The search for solutions that allow more efficient seed germination with less negative impact on the surrounding ecosystems is of paramount importance. Furthermore, crab is a valuable crop in many regions of the world, and optimizing its germination and growth benefits both farmers and end consumers. Finally, the main objective of this project is to make a significant contribution to the knowledge and application of sustainability techniques in agriculture, specifically in the germination process of the seeds of Rabanitus sabitus. Materials and methods. In this article, it will be constructed considering the methodology structure, the materials to be used, and the presentation of the result obtained. In addition, aspects such as information technology, electrical design, and mechanical design will be addressed in a comprehensive manner. It is considered appropriate to use the German methodology BDI 2206, thus research as a practical guide for the development of innovative mechatronic product systems. 2. rapid prototyping, employed for efficient development and testing of the systems. 3. Multidisciplinary approach integrates electrical, mechanical, and electronic design aspects. Morphological matrix. The generator tool is a detailed description of the generic morphological matrix basket, where each aspect is broken down into individual tables showing both the sub-characteristic and the corresponding data source. The project uses morphological matrices based on n-dimensional morphologic boxes. This tool details key designs, aspects, and supports the design process by mapping products' attributes. Definition, careful definition of essential design components, alternatives, listing different options for each identified feature. Interconnection, graphical representation of links between products' attributes. Function structure. The system functions are grouped into 4 domains: control, electrical, electronic, and energy. Each domain has specific responsibilities in the overall system operation. 1. Control domain manages the overall system operation and decision-making processes. 2. Electrical domain handles sensor, control system, and actuator drives. 3. Electronic domain responsible for sensing analysis, comparing, rectifying, and feedback. Energy domain manage power distribution and driving functions. Seat structure design. Well, the design features a double chamber planter. One compartment stores water, while the other holds the substrates and seats. These setups ensures optimal humidity and controlled irrigation. 1. Water compartment stores water for gradual release to the substrate. Substrate compartment houses seeds and nutrients for elimination, and interconnection allows controlled water flow between compartments. Control structure. The electronic control structure is crucial for monitoring and regulating the germination environment. It includes sensor and central control system and automatic adjustment mechanism. 1. Sensor monitor humidity and temperature conditions. 2. Central control processes center and makes adjustments. Actuators implement change to maintain optimal conditions. Electrical design. The electrical system integrates various components, including an Arduino One for control, a motor for irrigation, relay modules, and LED strip with ultraviolet diodes. Components: the relay module, quantity 3, power consumption 1.35 watts, component pump, quantity 1, power consumption 1 watts, component LED strip, quantity 1, power consumption 8.4 watts. Component Arduino, quantity 1, power consumption 0.075 watts. Finally, final assembly and simulation. The complete assembly integrates all components into a cohesive system. A digital simulation in Tinkercad provides a comprehensive view of the assembled device and its functionality. Physical prototype, 3D printed model of the germination device, digital simulation, Tinkercad visualization of the electronic components and connections. That's all. Thank you all.
Okay, thank you for the nice presentation. Next for the question for all the our participants. Is there any question or comment for this presentation? No? If no, my question for Mr. Manuel is this simulation is run or not yet? Because we not see the result of the simulation.
Actually, I practice this simulation. Actually, it's work.
Okay. If the simulation if is work, it will be
Yes.
better if you put a photo or graph or table. It will help to explain. Just a suggestion. Okay.
Um,
Any
it
comment?
works in Former.
Ah, okay. Yes, that's my suggestion. If you give a picture or graph or table, it will be better. Okay, that's all I think. Okay, thank you very much for your presentation, Mr. Manuel. And for the next presenter, I think you are the presenter, right?
Yes.
Okay, okay. You can continue for the next paper with title of Automated Hydroponic Irrigation System, Innovation and Efficiency in Lettuce Cultivation. Okay, you can continue to the second paper.
Wait a minute, please.
Okay.
Well, good afternoon. Thanks the first international conference on industrial electronics, robotics, and informatics for the kind invitation. Well, I'm in charge of the presentation of the research entitled mm, Automated Hydroponic Irrigation Systems, Innovation and Efficiency in Lettuce Cultivation. The research are Kerry Moscoso, Luis Visurraga, Wilfredo Paco, Edson Jurja, and Joaquín Machaca. Well, irrigation is essential activity in agriculture, and its efficient management is crucial for the healthy develop plants, especially in hydroponic systems. This paper presents the design and development and automated hydroponic irrigation system optimized for lettuce cultivation using advanced technologies such as sensor and control systems based on a black box simulation model. The system allows precise water and nutrient management, ensuring ideal conditions for plant growth. The methodology applied in the design of the system is based on the BDI 2221 standard, which provides a systematic approach to the identification and resolution of engineering problems. Tools such as the morphological matrix and functional diagrams were used to optimize the functionality and efficiency of the design. The result shows that the automated system offers superior control of water and nutrient distribution, contributing to a more sustainable and productive growing environment. The system includes a charge controller to prevent battery overcharging, an on-off circuit for the submersible motor pump, and DC converter to the power Arduino board, of which are integrated to ensure automated and efficient operation. In addition, the mechanical design has been optimized to facilitate maintenance and ensure the durability of the system. This works contributes to the advance of hydroponic agriculture by offering a technological solution that improves irrigation efficiency and promotes sustainability in agricultural productions. Well, irrigation is a fundamental activity in the agriculture, as plants requires water for their growth and development. This need is shared by traditional agriculture as well as hydroponics and gardening. In certain cases, water supply can be straightforward, such as when rainfall provides the necessary amount. However, in most situations, this is not sufficient. Historically, agriculture was carried out near rivers and lakes to facilitate access to irrigation water. However, the expansion of civilization forced farmers to move away from these water bodies and to develop various irrigation techniques. In Mexico, for example, irrigation water use efficiency is alarmingly low, with application efficiency below 40% in most irrigation districts and modules, resulting in large water losses. This underlines the importance of implementing more efficient irrigation solutions, especially in systems that rely on limited water resource. Hydroponics, which uses irrigation accompanied by nutrient solution for integrated plant development, is presented as a promising alternative for agriculture in controlled environments. However, the success of hydroponic cultivation depends to the large extent on precise and continuous irrigation management. Problems such as lack or excess of water, humidity, temperature, or pH can seriously affect plant development. Overwatering, for example, can lead to root and the development of unwanted organisms such as fungi, underlining the need for careful control. This project focuses on the designs of an automated hydroponic irrigation systems that optimizes water and nutrient management, promoting healthy plant growth. To achieve these advanced technologies will be employed, including sensor control system and precise distribution mechanisms, such as drip irrigations. These components will be fully integrated, allowing for automated, responsive, and real-time adjustment according to the needs of the group. The purpose of this article is to present a technological solution that improves irrigation efficiently in hydroponic systems, ensuring ideal condition for plants development and contributing to the advancement of a sustainable agriculture. This methodology used is based on the German VDI 2221 standard. knows for its systematic implementation. First, problem identification, define irrigates challenge in hydroponic lettuce cultivation. Two, conceptual design, develop initial system concepts using morphological matrix and black box model. Three, detailed designs, create detailed electronic and mechanical designs for the automated systems. And four, implementation, construct and integrate system components for optimal performance. Here present black box simulation models. Inputs, electrical pulse, energy, water, and nutrients enter the systems. Proceeding internal mechanisms optimize resource utilization for plant growth. And outputs, voltage variations, modified matter, and nutrient fortified water exit the system. Morphological matrix application. The morphological matrix serves as a powerful tool in the design process of the automated hydroponic irrigation systems. This systematic approach allows for the exploration of multiple designs alternatives by breaking down the system into the core components and functions. Each function is associated with various possible solutions, creating a comprehensive matrix of design options. By utilizing the matrix, the research teams can systematically evaluate different combinations of components and technologies, leading to innovate and optimize design solutions. These methods ensure that all potential designs variations are considered, promoting creativity while maintaining a structured approach to problem solving. Electronic system designs. One, battery charge control prevents overcharging using a relay and 555 timer circuit. Two, system on-off Arduino controlled systems with joystick interface for pump operations. Three, power supply, DC-DC converter provides stable power to the Arduino board. Mechanical design components, supporting structure, stainless steel frame with vertical columns and horizontal beams for stability. Irrigation systems, rail-mounted distributor head with adjustable nozzles for precise water distributions. Cultivation trays, perforated trays for efficient drainage and optimal root environment. Control system integrations. One, sensor data collection. Gather real-time information on water levels, pH, and nutrient concentrations. Two, data processing. Arduino-based system analyze sensor inputs to determine optimal actions. Three, actuator control. Systems adjust pumps, valves, and nutrient dispensers based on processed data. System efficiency and sustainability, water conservation, recirculation system reduce water usage but up to 90% compared to traditional methods. Nutrient optimizations, precise control ensures optimal nutrient delivery, minimizing waste and maximizing growth. Energy efficiency. Solar powered components and efficient pumps reduce overall energy consumptions. Future developments and implications. Well, the automated hydroponic irrigation system for lettuce cultivation represents a significant step forward in agriculture technology by integrating advanced sensors, precise control mechanisms, and efficient water management. This system addresses critical challenges in modern farming, such as water conservation and crop optimization. Looking to the future, this technology has the potential to revolutionize urban agriculture, enabling high yield, resource efficient food productions in space constrained environments. The system modular designs in adaptability make it suitable for scaling up to commercial operations or down to household units. Potentiality democratize access to fresh, locally grown produce. AI integration first, machine learning algorithms could further optimize grow condition and resource usage. Two, scalability system designs allows for easy scaling from small to large scale operations. And three, urban agriculture. This technology could revolutionize urban farming, increasing food security in cities. That's all. Thank you. Wow.
Okay, thank you for Mr. Manuel. Again, is there any question for this presentation? No one. Then again, my question is this simulation or real-time implementation, or you implement it in real hardware?
In both cases, our work in a farm in Peru.
Okay. Just the same situation. If you do experiment or simulation, it will be better if you give a picture so that we see what you do. Okay, thank you.
Thank you.
Okay, that's enough for Mr. Manuel. Thank you very much for your presentation. You can close your share screen, please.
Yes.
Then for the next presentation is about the design of PLC control sheet metal folding machine. Then for the presenter, you can share your screen. The author is Cesar Xavier, Christian Luis, Wilder Filalfa, and Manuel Michael Brown. So, Mr. Manuel, the third paper, you will present the third paper again. Oh, okay, different person. Okay.
Can I start my presentation?
Okay, let's start.
Of course. Best regards, everyone, and thank you for joining me. Today, I'll be presenting our project titled Design of PLC Control Sheet Metal Folding Machine. The goal of this project is to create a foldable hydraulic press controlled by a programmable logic controller, or PLC, specifically designed for small business in South America. In countries like Ecuador and Peru, small companies face challenge in automating metal bending due to high cost. This project aims to develop low-cost machines to make metal folding accessible to these companies, allowing them improve productivity and reduce operational costs. Automatization has a transformer metal bending process around the world with semi-automatic hydraulic pressers, including the CNC machines, providing a high precision and fast production. However, in Ecuador and Peru, the available of semi-automatic folding machines are still very expensive for a small business. Our objective here is to offer an affordable yet effective solution for these companies. This folding machines is designed to increase production efficiency and reduce manual labor, and helping small business and stay competitive. For the part of material and methods, our folding machines operate in two modes, manual and semi-automatic. In manual mode, the operator uses two pedals. By pressing the start one pedal, the piston is activated, and pressing the stop pedal disactivated. In semi-automatic mode, pressing the start 2 allows the piston to extend and retract continuously until the stop pedal is pressed. This flexible control makes it easier for operator to choose the best mode for their task, improving efficiency. Additionally, the machine includes an emergency stop button, providing a crucial safety feature. Figure shows the operation of the programming in letter language. This shows the correct control of the machine from startup and shutdown in both working modes. These machines' features are temperature control system to monitor and maintain a safe operating temperature. When the temperature gets too high, sensors detect it and cooling fan automatically activate. This cooling system is essential for preventing overheating, which can cause maintaining a stable temperature is critical for consistent performance, specifically for long production runs. According to the simulation in Factor IO, to ensure the effectiveness for our design, we create virtual simulations in Factor IO. These simulate control panels, includes four main control buttons, pilot lights, and dedicate emergency and stop buttons. There are also two green buttons, let the operator selects between manual and semi-automatic mode. These simulations allow us to observe how the machines operate under both modes and test the control features before building and fixing machines. The feature shows the temperature control simulation in Proteus software as the temperatures increase. In additionally to Factory IO, we use Proteus software to simulate temperature control systems in this model. The fan automatically responds to rising temperature when machine's temperature reaches 45 degrees Celsius, and LED starts flashing as a warning. As 55 degrees, the LEDs remain solids and the fan operates at fully spent to cool down the systems. These features ensure the critical components like the motors and punch are protected from overheating. Now let's look at the machine's physical design. The machine stands 200 centimeters, tall 70 centimeters, wide and 250 centimeters long, with a capacity to handle metal sheets up to 120 by 240 centimeters, 20 by 240 centimeters. Figure shows the design of complete machines, including the die holders, die punch holder, cylinder base, also the hydraulic cylinders, and including the PLC rotating structures. These dimensions were chosen to ensure the machines has the stability and strength required for hydraulic operations, meeting the common needs to small scale industrial applications. Comparison with previous research, such as the by Nicela and Pañarreta, as well as Avila, has focused and designed hydraulic folding machines to improve in efficiency and safety. However, their designs are expensive and tailored for large companies, or approach is different. As we integrate a mechatronic control system with PLC, proximity sensors, and temperature control circuit, these features improve efficiency and safety, but keep the cost low, making the machines a flexible option for a small business. In conclusion, our testing shows that these machines reduce both production times and physical effort. In comparison, manual folding can take 5 of 10 minutes, while our machines completes the same process in just 10 seconds. The hydraulic systems also distributes force more evenly along the punch, improving the quality of each fold over these machines. Represents efficient and economical alternative to expensive or manual folding method. For recommendations on the future, we recommend that the materials used in construction be careful check to match those specific in this study. This ensure optimal performance based on the calculate trickless and mechanical properties. In Thank you for all, and that's all.
Okay, a nice presentation. Then is there any question for this presentation or comments? And I want to remind all participants to fill the attendance form. I have sent the link in the chat. You can open the chat and fill the form. And if there are no question, my question is from me. Uh, this design is just simulation, or you already make the real hardware from for this design?
Design is tested through simulations in Factorio and Protest software, allowing us to verify the control and temperatures monitoring systems. This simulation
Uh,
showed the machines could operate efficiently in both manual and semi-automatic modes.
okay, then based on your opinion, is it possible to make the real hardware of this design?
The results indicate the machines could reduce productions time significantly compared to the manual methods, uh, confirming it is an effective solution for metal bending in small business.
Okay, very interesting. Thank you very much, Mr. Christian Luis Lopez. And that's enough for your session. You can close your screen sharing. And then we will go to the next presenter with the title Enhancing Financial Institution ATM Operation Through Service-Oriented Modeling Architecture. So, a case study. Then please share your screen for this presentation. Don't forget for all participants to fill in the attendance form. Okay, you can start your presentation.
Oke, Thank you, Pari. Good afternoon, ladies and gentlemen, distinguished speakers and participants. It is a great honor to be here at the International Conference on Industrial Electronics, Robotics, and Informatics 2024. My name is Ayer Fauzan, and I am a master's student in the Information System Management Program at Binus University. Today, I am delighted to present our research on enhancing Financial Institution X ATM operation through service-oriented modeling architecture. It's a case study. This study is collaborative effort with Mr. Gunawan, and we are eager to share our findings and insight with you. We hope to contribute to the ongoing discussion and advancement in our field. We will explore how SOMA can improve ATM services by addressing various challenges in the current system. To give you some background, in today's technological revolution, enterprise architecture plays a crucial role in managing complex systems within a large organization. Frameworks like TOGAF are essential for designing and simplifying these systems. Companies often face challenges in aligning technology with business processes due to market pressures and technological advancement. Service-oriented architecture, or we know it as SOA, offers solutions by enabling faster and more cost-effective system management. And this research focuses on applying SOMA to ATM modules, aiming to enhance flexibility, scalability, and integration. Moving on, the next slide, we are discussing about the objective and methodology. The primary objective is to enhance ATM operation at Financial Institution X using SOMA. This involves mapping existing business processes to identify inefficiencies, designing a more efficient business model, and evaluating the effectiveness of SOMA. The research employs a descriptive, qualitative approach through a case study involving data collection, business process mapping, design and implementation, and evaluation. The first stage in the SOMA method involves describing the scope and the ongoing business processes within the core banking system at Institution X. This results in re-engineered management processes. The CBS application, particularly in ATM modules itself, it's divided into account management and transaction management, covering activities like account opening and foreign exchange transactions. The aim is to enhance the operational efficiency through the re-engineered process. Next step is solution management. The solution focuses on addressing challenges such as the lack of 24/7 payment services and difficulties with exotic currency transactions. SOMA, we trust to provide real-time service capabilities, and improve transaction reconciliation. A structured overview of challenges and proposed solution is presented to guide the implementation. Moving on the next slide, the key service identification techniques are used to define the strategic goals and metrics, such as offering 24/7 payment services and broad currency option for foreign exchange transaction. This would help tailor services to meet customer needs effectively in Institution X. On the right side, the specification page will detail the service component necessary for ATM operation, clarifying their relationship with data and processes. Each component is described for easy implementation, ensuring readiness for integration into the system architecture. We also leverage the existing assets and further elaborate the services, flows, and component for the identification phase. As we have seen in the previous slide, leads us to the realization phase that connect to various services identified and developed in the previous stages into a cohesive service-oriented architecture reference model, which is tailored for the CBS at Institution X. This model consists of several layers. The consumer layer is the layer that includes interface that facilitate interaction between customer in the CBS. And the CBS is a central hub in this case. It ensures seamless integration with external systems, enhancing user experience and accessibility to banking systems. Business layers defines the core business functionalities and processes, ensuring that operation align with the strategic goals and customer needs. This alignment is crucial for maintaining operational efficiency and customer satisfaction. Moving on the service component layers, it's break down services into more granular component, allowing for efficient management and execution for banking operation. This granularity support better scalability and flexibility in service delivery. On the bottom side is an operational layer, will support the underlying operation necessary for executing business process and maintaining data consistency. This layer ensures that all technological and operational aspects work harmoniously to support the institution objectives. In conclusion, our research indicates that implementing SOMA at Institution X has significantly enhanced the efficiency and integration of ATM operation within the CBS. The key outcomes include improved business process transformation, addressing operational challenges, and facilitating the integration of various payment channels like BFAS and the ERP. And for the future research, it is recommended to focus on quantifying the benefit of SOMA, conducting comparative analysis with other architectural frameworks, and performing longitudinal studies to assess long-term impacts. Strategically, the institution should focus on strengthening its human resources, adhering to regulatory standards, and conducting periodic evaluation to ensure sustainable SOMA implementation, thereby improving operational performance and adapting to the evolving digital banking landscape. And well, this brings me to the end of my presentation. Thank you for your attention. I'm happy to answer any question you may have. Thank you.
Okay, thank you very much, Mr. Ayar. Is there any question? If no, maybe from me. My question is, in your proposed method or model, do you have parameter to show that your proposed model or method is better?
Yeah, sure. We are using we are using the SOMA frameworks that will become our indicator or the guideline for our research. And but the limitation of this framework is didn't have any quantitative aspect for indicating the result if it is fits or not. So we are in our research, we are doing in a qualitative approach, and we are asking the source to ensure that this framework or this SOA architecture framework that we are providing, it's fits for the institution X.
Okay. Thank you very much for Mr. I. And I think this is the end of our session. Maybe before we close our session, we can take picture together. The participant who still in the Zoom, you can open your camera, and for the committee, you can Mr. Cesar or Christian Luis. Do you still hear? No, I think it has okay. You open your camera, Mr. Cesar Xavier. Okay, we can take a picture together. One, two, three. Okay, again, one, two, three. Okay, thank you very much for joining ICIERI 2024. And for the next information, just with the committee information. Thank you and good afternoon, everyone.
Thank you,
Thank
Pak
you,
Ali.
Mr. Ayer. Okay.
Bapak untuk asesmennya bisa dikirimkan Bapak kalau sudah selesai.
Baik, tunggu sebentar saya kirim di chatnya ini ya.
Baik Bapak.
Tunggu sebentar loading.
Iya Pak.
Oke, sudah terkirim ya? Cek dulu sudah terkirim. Halo?
Sudah Bapak. Terima kasih Bapak.
Oke, baik. Saya Lidum. Terima kasih.
Terima kasih Pak.